Hi everyone, welcome back to my channel. My name is Prakash Duhun and today we're going to talk about a couple of things. First, we're going to talk about something called as a pigeonhole principle. Okay, and in this principle what we do is basically we have k number of holes and they're t into k plus 1 pigeons. And using this principle what we come up with is this condition which is basically always satisfied irrespective of how these pigeons choose their different holes to go inside. Okay, so we're going to learn a little bit about that further into the video. And after that, we're going to also look at one of the questions, which is sock search, in which you have different numbers of red, yellow, and blue socks. And, the number is not known. And we're required to find out how many socks, and these are single socks I'm talking about, you need to pick out of this bag in order to find a pair of socks. Okay, so we're going to learn more about this shortly. Stay tuned till the end. And before that, if you've not subscribed to my channel so far, please do so. I highly appreciate your support in this regard. Okay, so now let's talk about the pigeonhole principle. So it's a very simple principle. What it basically says is you have, let's say, k number of holes. Okay, so these are different holes as we can see on the screen, represented the first hole, second hole, third hole, all the way to the kth hole. Okay, so these are k holes, and let's say there are tk plus 1 pigeons. So one thing to note is tk basically tells us that this part is nothing but a multiple of k. Okay, so let's say if k was 5, then tk could be 2 into 5, 10. It could be 3 into 5, 15, or something like that. Okay, but we don't have tk, we have tk plus 1 pigeons. Okay, now what we're saying is, let's say these pigeons randomly go and sit in one of these holes. Okay, what this principle says is, it says that there has to be one hole where there are at least t plus 1 pigeons. Okay, or in other words, at least t plus 1 pigeons share one or same hole. So let's try to just understand a bit what's happening here. So let's say if all the pigeons just randomly sat in hole number 1, and I'm assuming the capacity is infinite, right? They're a deep hole. So let's say if all of them came and sat here. So is this principle still valid? The answer is yes. Why? Because there's one hole, which is hole number 1, where all tk plus 1 pigeons are here. And it says at least t plus 1. So we're more than t plus 1, so I think it's sufficient. Okay, so great. So you may say that, okay, this is a great case, but it's a very easy case. Let's try to find out the worst case. So the worst case is that, the pigeons, they are very sensible and they occupy the holes uniformly. Okay, so if they say, okay, one is more occupied, we'll go to second, or and vice versa, and whatever. Okay, so what's going to happen is the first TK pigeons, they're gonna go in these holes in uniform fashion. So as a result, what's gonna happen is each of these holes will have T pigeons, because if you have T pigeons here, you have T pigeons here, all the way till here, then if you sum it up, it's basically T plus T plus T till K times. This is K times, and you have TK. These are all the pigeons, and we say they're sensible, they go uniformly in. Okay, now but there's one last pigeon here. Now this guy has to go somewhere. And where would this person go? They have to choose at least one of these holes. So let's say they choose hole number 3. So now this pigeon, they will come and sit here. And suddenly what you will see is there's this hole here where you now have t plus 1 pigeons here. Okay, and I'm just going to quickly erase for cleanliness. Okay, so now what you see is all the other holes have t pigeons, right? But this hole here has t plus 1 pigeon. And let's just check if our principle is still valid. It says at least t plus 1 pigeon share one or same hole. Or in other words, you can say there's at least one hole where you will have t plus 1 pigeons. Okay? And in this case, this is true. This is hole number 3. Okay? So this is the pigeonhole principle. Very simple. You can consider both extreme cases where everybody just goes into one hole, which is easy case that has to be satisfied. This formula gets easily satisfied. And the other case is when principle gets valid, but it gets barely valid, I should say, and because there's just one case, and this is what it says, there's at least one or same hole where this will happen. Okay, and this is what we're saying. So in one hole, you'll find this situation happening. All right, great. So I hope you understood this right, and now we're going to go into one of the problems. Okay, so the problem is it's a sock search problem, and you have basically 3 kinds of socks. You have red socks, you have blue socks, and yellow socks. And you could think of a box like this. Okay, so I hope you can get to the idea. Basically, this is a fair, I would say, a vague representation. There's a box here, and there are all kinds of socks there, and they're not necessarily supposed to be in pairs. As you can see, red could have three, blue could have a pair, yellow could have a pair here, but that's okay. I mean, we're keeping it very general, okay? Let's say you have X red socks, Y blue socks, and Z number of yellow socks. So what we're supposed to find out is we're supposed to find out the minimum amount of socks that you need to grab from this bag in order to find a matching pair. So what is this telling us? Each of these socks, when I say X socks or X red socks, they are individual socks. They're not a pair, right? And similarly for Y blue socks, there are Y number of these single socks. They're not just a pair here. And we were saying we blindly grab some of these socks from this bag, and we want to understand how many socks do we need in order to make sure there's one matching pair. All right, so I'll probably give you a moment to think about this problem and try to solve it yourself. And of course, the hint is use the pigeonhole principle. All right, so now I hope you got to the answer to the problem, but if not, that's perfectly fine. We'll quickly do this. In this case, what's happening is we know that, okay, there are three kinds of socks, and let's just make, notations for them. Okay, so this is red, this is blue, and this is yellow. Okay, now let's say I grab N socks. Let's say I grab N socks. Okay, if I have these N socks, can I use them and put them in these boxes, which is red, blue, and yellow? And you could think of them like pigeonholes, and the number of socks you got as pigeons. The only thing now happening is each of these socks are going to go in their respective boxes. So if in N socks you, let's say, had 2 red, then all of them will go to red. 2 red will go here. If let's say you had 3 blue, blue will go here, and stuff like that. Okay, so we want to make sure, we want to now put all these N socks in these different boxes. And I would say now is a great time, if you couldn't solve the problem first time, to try to solve it and see how many pairs do you need. And start with small n, like smallest you need is 2, because that's what you need for a pair, right? And then increase it to 3 and so on. See, where do you find that the minimum amount of n is enough to get you a matching pair? Okay, so I hope you could have cracked this problem. Well, let's try to solve this. If you could not, that's perfectly fine. N is equal to 2, that's the minimum amount of socks you need for a pair. So what is possible situations here? That basically means you just grab two socks. One great case is, let's say you had 2 blue socks. Okay, and I'm assuming all these X is much greater than 2, and Y is much greater than 2, and similarly Z is much greater than 2. Okay, so it's simple, sane assumptions. So let's say, we took 2 socks and basically both of them are blue. So in this case, we have a pair already and both of them will go here. Great. But it is not the worst case. The worst case is you had 2 and one of them was red, the other was blue. Okay. In this case, red would go to red, blue would go to blue, as indicated like this, and blue would go here, and none of them would be a pair because, we don't have enough. Okay, so we clearly see that n is equal to 2 fails. Okay, now let's see what happens with n is equal to 3. So let's say if n is equal to 3, can we find a case where this also fails? The answer is yes. Let's say you had 3 socks, one was red, one was blue, one was yellow. In this case also you fail, you don't have a pair. Okay, so now let's talk about 4. Now, again, I'm going with the same analysis of worst case. So let's say the first 3 socks had red, blue, and yellow. They're different colors. What is going to be the 4th sock? It has to be one of the red or blue or yellow. So let's say it's blue, but suddenly now we have a pair. Okay, so this clearly tells us that 4 is the answer. And if you got it right, that's perfect. But now let's also try to solve this using pigeonhole principle real quick. So we know in pigeonhole principle, if you had k holes and tk plus 1 pigeons, then at least t plus 1 pigeons share the one or same hole. Okay. Here we had 3 holes. Okay. And we want to find out how many socks do we need. Okay. So we have 3 holes. The number of socks and socks is in our hand. It's in our hands how many we want. But we want this to be minimum. And we want to make sure that in one of these holes, the red, blue, and yellow, one of these holes, you have at least two socks. That's where you get a pair, right? So if you remember the pigeonhole principles, k is equal to 3 here,
Okay, tk plus 1 is n. And then what we need is the principal said at least t plus 1 pigeons are going to be in one hole, share one hole, right? At least one. Now we know t plus 1, we want it to be 2. This implies t is equal to 1. Okay, perfect. If t is equal to 1 and k is equal to 3, then we can easily find out n is 1 plus 3 into 1. That is equal to 4. So using the pigeonhole principle, you can directly find n has to be 4. But we've already found the solution using intuition. That's perfectly fine as well. And you can also directly use the formula to get to this answer. So I hope you got to the answer. And if you did, that's perfect. Cheers to you. All right, so I hope you enjoyed this video, and if you did, I would request you to please like it. Also, share your comments about what you thought about the problem, and if you could crack it, and if that was the case, that's awesome. I want you to see all of you really come up to speed and be able to solve these problems even without looking into solutions. And if you're not able to do that, that's perfectly fine. First time or second time, you probably need some support, but with repetitive attempts, you can definitely become a master of these problems. All right, so see you next time. Until then, take care.